that's 160. 160. 0.000398 square. Square divided by 1.48. 1.07 minus 5. That was 160. So it will be just 1 minus 5. Did you get the same number? Okay. So the pH of the solution that is 0.10 molar concentration acetic acid and that's sodium acetate. So we have acid here and we have conjugate base. Anytime you have conjugate pair, you use Henderson-Hasselbalch equation as a shortcut. Okay. So pH is pKa plus logarithm acid conjugate base. Ka value is given right there. pKa means minus relative log of pKa. Log HA concentration, X concentration is right there, 0.1. And base concentration is 0.1 as well. And we have more number. This will be just 1. Log 1 is just 0. So your pH will be just that guy. Negative log 1.8. 5, 4.74, 260 pH. Calculate the equilibrium concentration of format ion in solution which that forming acid and that Ka for that is this. So they are asking equilibrium concentration of.
I'm sorry, the last one. Does the second log not get a minus?
No, the formula has a sign there.
Oh,
Be
okay.
careful. Be careful. If you write equation as pKa first and pH, that will be minus. You memorize formulas like that, but sometimes they ask pKa, then you can rearrange, then you're going to have a negative sign. Okay?
Thank you.
Calculate the equilibrium concentration of formate and in solution which is that forming acid and HCl. Alright. So at initial condition we have this weak acid, this amount. At the same time, we have that guy, which will provide common ion of hydrogen ion, 0.079. This provides chloride ion as well, but it's nothing to do with this equilibrium. So that's initial condition. If you know initial condition, you can find out at equilibrium 0.412 minus x, 0.079 plus x, plus x. So my Ka 1.8 minus 4 is equal to x times 0.079 plus x over 0.412 minus x. But you can approximate x can be negligible. So finding x will be, calculation 1.8 minus 4 multiply 0.2 divided by 0.079. That will be our x. What's x? X is that. And what are they asking? They're asking equilibrium formic acid, this guy, which means they're asking actually x. At equilibrium, Consider that guy is x. So they are looking for x. So this will be your answer. Okay? You have to calculate it. This might be a little more challenging. This will be challenging, more challenging than any other problem. We have certain exit, this much, and you have conjugate base, this much. So whenever you see conjugate base pair, conjugate pair, you just think Henderson-Hasselbalch equation. This is exit. Again, I'm going to use that formula. So PH is pH. Because I'm going to use pick up again, so I have to throw away. pH, pKa. So pKa. I'm going to use that formula right away. Okay. So negative log pKa plus log concentration of HCa. I say A minus. But the thing is, we cannot use this one for exit and then for here. The reason is that we're gonna mix these two solutions together. So we no longer have that concentration because you're gonna mix it. So concentration of A minus is you multiply those two guys. So this concentration will be 200 milliliter times 0.10 divided by total volume 200 times plus 100, which is 300. That's concentration of this guy. Concentration of this guy is HA. What is HA? Wait. What did I do? So that is this guy. I just switched it. So HA is this divided by 300. For base is 0.10. It's the same? Wait, what did I do? I think I did it right. Okay. So exit 0.20. Oh, I'm sorry. 2 and 100. Oh, seems like it's right. The base is 200. Okay, right. But then this is a common factor, so you can just cancel it. So in the end, if you see, if you multiply, that will be the same, right? This will be 220 millimole. This guy also, if you multiply 20 millimole, so that will be just 1. So that actually become very simple. You're gonna have only this number, only this guy. So it's not that hard after you do this algebra. Calculate pH of both that contain that guy with this. So we have exit again, conjugate base. It's the same thing. So we are using Henderson-Hasselbalch over and over. So I'm gonna skip it because it's the same thing. There's nothing new there. Any question? Seems like actually many of you do pretty well. I saw your score. Many of you have not, or half of you just having full score. let's see how buffer act. So buffer is you have a conjugate active base pair together, and they should be weak stuff, not strong stuff, right? So as an example, hydrofluoric acid is weak acid, conjugate base is fluoride ion. So as long as we have certain amount of both, we call them as a buffer. It doesn't have to be equal amount. So in this diagram, it's just saying as concentration, when you have in the solution, we have equal amount. So we same concentration of both. That's ideal buffer, but that's not required. Let's just we have equal amount. And then if you add in buffer system, if you have add a base. So this is like a human body, and somehow accidentally they drink strong base. And accidentally. So then, actually portion of this guy will neutralize incoming base. So let's say we add this amount of base to the human body, then we're gonna use up that amount to neutralize that guy. And then as you can see, incoming base neutralized by acid. Then this guy give proton to base, make water, and then we produce conjugate base. So if you drink a little bit of base, you may lose a little bit of HF, and then make a little extra of F minus. So there will be a little bit imbalance. But this is still considered buffer. It is still work. Okay? After you drink a little of hydroxide, somehow you can drink even more. Okay? And it's not okay, but that's how buffer works. Or accidentally just got some injection of acid. This time, incoming acid will be neutralized by base portion of buffer. And then that combined to acid. So this time, conjugate base is used, and then your acid will increase. So this change will cause a little change in your pH, but it's not by much. The reason is that if you remember Henderson-Hausdorff equation, pH is pKa plus logarithm HA A minus. Okay. Now assume your body is not a buffer system. It's just water and lots of chemical, but not buffer system. If that's the case, somehow somebody who try to kill you inject 0.1 molar acid in your body, then your pH will change because pH is negative log of H plus. Your pH will change by 1. Why? Because negative log of 0.1 is 1, right? So your body, let's assume, make simple. Your body is 7. It's not 7, but let's assume 7. After that injection, your pH will drop at 6. In biological system, pH change 1 is really, really bad. I don't know how bad, but it's really bad. Okay? But if your body is just more than water and other molecule, actually our body is buffer system. Then, if this change is coming from outside 0.1 molar concentration, then you can say the other amount is like 1 mole, something like 1 mole, right? So we can see originally 1 molar of base, weak acid conjugate base is 1 molar. And then if you somehow somebody inject acid to kill you, then because it's acid, your base is used, become 0.9 molar. This one become 1.1 molar. So using that, now your pH will be pKa value log HA A minus. pK doesn't change because the equilibrium constant, it doesn't change. But HA is now 1.1, this is 1.9. If you take logarithm of this guy, what is it? Log 0.9 divided 1.1. Okay. 0.087. So your pH should be now 6.913. Okay. So having buffer system make your pH almost still same, right? Not much change. That's why buffer system is important. So you can see that Handels's equation without buffer, this is just change at negative logarithm. But when you have buffer system, it will be this ratio. Okay? Because of the ratio, whatever you have changed, that is between ratio of total amount. So that makes pH change a bit very like a small change. But they can still kill you. For example, amount they put is like, let's say this was 1 mole and 1 mole. Well, if they put actually like a 0.5 mole or 0.7 mole, then you're gonna have lose about this amount, right? Then your pH will change to almost like that. So, I don't want to have too much exploration device. Okay. So this is buffer. Why? Because you have weak acid, carbonic acid, and conjugate base bicarbonate. So if you add H plus, what kind of reaction will happen? Actually, this is actually our body system. Body use carbonic acid and bicarbonate. This is what we have in our body system. So in reality, if you have H plus somehow in your body system, that will be counted by base. And then neutralize as this. And everything is aqueous. The same system, so again our body system, somehow we have we drink like cleaning detergent something because they are all base. Then this will neutralize by H2O3. Make it water and the bicarbonate. What about this? This is also ammonia weak base, conjugate acid, so it's a buffer again. So incoming actually should react with base portion of buffer. Which one is base? What base do I have? Ammonia. Ammonia is base that will react with incoming acid that will turn into ammonium ion. If OH hydroxide incoming species, then it will react with acid portion of which means ammonium. And then they will react water and ammonia, so actually ammonium hydroxide. Yeah. Or maybe you could write as water and ammonia. So this is also possible question. So because when you have certain incoming acid-base component and how they react to buffer, you should write down. Write down the reaction. So we did that like when you add acid base to our body system, how pH change. So I already used Henderson equation to see how pH change. We're gonna do a little more like we're gonna do a little formal calculation. Let's see. So why don't you try to find out pH of this buffer? So we are not doing this problem yet. Do you have buffer that is made of base portion and conjugate acid? What's the pH right now? What's the pH of this buffer? You can use Henderson's bar. Why don't you confirm that pH is 9.08? And you confirm, if you do this calculation, you get pH of 9.08. Yeah.
This is gonna be a dumb question, but how do you identify like the A minus and the HA again?
So HA is supposed to be acid, A minus be base. When we have ammonia and ammonium, which means this will give us this guy. between two, we're going to identify which one is base, which one is acid. So this is not a typical acid, but when we compare between these two guys, this is more obviously base, this is conjugate acid. So in this equation, we use conjugate acid here, base there. Okay. Does anybody have the same number, 9.08 pH? Okay. Right. So that is before you add anything else here. So that is from buffer solution. So assuming that this is somebody's body, not human. Human pH might not be that, but some animal or some other some life form has this pH. And then with some cruel guy add this base or acid to their life, and then see how pH change. Okay. So after adding hydroxide, that's an answer. We add hydroxide here. So we can say ammonium have equilibrium with ammonia. And this. Before we add this guy, how many more of ammonium do we have? Well, we have ammonium with that concentration, and this one has that volume. So if I multiply, I have 400 milliliter times 0.300. I have that many amount of ammonium. What about ammonia? 0.200 in same amount of solution. So this is before adding NaOH. Okay. Now we are adding NaOH. How much? 10 milliliter of that concentration. So ammonia, no, not ammonia. So base is we are adding more of hydroxide 100 milliliter times 0.0500. So that will be just if you do calculation 120 millimole. Okay, 3 sig feet, 4 sig feet. I have to have 3 sig feet. Okay. If you multiply this guy, it will be 80 millimole. 3 sig feet, 4 sig feet, I have to 3 sig feet. You are adding this much of base. If you multiply 1,1,1,1,5 millimole. 2 sig feet? No, 1 sig. Oh, 3 sig. 3 sig feet, 4 sig feet. So it's 3 sig feet. Okay. Are you familiar with molymole?
No.
So when you have molarity times liter, they become more. If one of them are either millimolar concentration or milliliter, then you can just take milli in front of it, and then m times L. And m times L is more, so that will be millimole. Okay. So if I use this guy, so this is somebody's life system, and the incoming hydroxide should be neutralized by this goes to base. We're going to use acid. Okay. you have both of them in your body. This will neutralize the incoming base. Because of that, after adding hydroxide, 5 will be used. So 100 minus 5, which means 115 millimole will remain as ammonia. But 5 millimole of ammonia will be turned into conjugate base. So I'm going to have here this plus 500, which means 85 millimole. So after we inject base to this system, now we have a new amount of conjugate pair. Okay? What we need is concentration. This is millimole. We need concentration. Okay? We need concentration. Concentration is mole divided volume. So concentration at so now we start icebox. Concentration of this guy is 115 millimole divided by volume. The volume is, you used to 400 milliliter, but you add 100 milliliter. So total volume is now 500 milliliter. So 500 milliliter. For this guy, you have 85 millimole. Total volume is again 500 milliliter. By the way, there is extra zero. I use extra zero. Now, milli and milli prefix will cancel. So mole over here is simply molar constant. Same goes here, and the molar constant. Now let's calculate. 115 divided by 500. 2.50. 1, 2, 3, 360. I need one more. 85 divided by 500. 0.17. Again 360. I need one more. So end of this titration, end of this neutralization. Now is just beginning of icebox. We just found the initial condition of our body system. This is beginning of icebox. That is initial condition here. But what are they asking? They're asking pH change. Okay. So we could use icebox, but since we just spend a lot of effort doing this, let's just use Henderson bar. Okay, make it simple. So pH is pKa plus again HA, A minus. So Ka value of exit. We do not have Ka value of exit, we have Kb. But we did calculate Ka value using water ionization here. So we can use that one as Kb, Ka. So we do have Ka, negative log of 5.555 minus 10. We are using that result over here. And oh, I missed the log. The log now original formula of this is actually equilibrium concentration. Okay? If you remember how we derive this equation, this constant is supposed to be equilibrium concentration, but the change is minimum. So you can assume this is just equilibrium concentration, and just initial concentration. Which means we can use this initial concentration for exit here and base here. Okay. negative low, 5, 10, low, I got 9.12. Why 9.12? Because there's a 260. So answer should be 9.12. So that is the pH. That's the pH when this creature or whatever receive get injection from this much of base. Okay. So how much did it change? Later pH was this, previous pH was that. That difference is just 0.04. Not much change. Okay, not much change. So you are using Henderson equation twice. One for original buffer, the other one for after you're adding that. But you cannot use directly because you have to go through, before you use Henderson-Hasselbalch, you're going to have to go through this step. This step is just neutralizing step. So incoming base is neutralized by conjugate acid. That will change amount of acid base, and the volume also change. So that we have a new concentration, and that's used in the Henderson-Hasselbalch. Okay. Why don't you try this one? Only difference is now this creature getting acid instead of base. Okay? So there will be difference. But why don't you try this? you get 9.03? Anyone have different number? Any question? Yeah.
In that one, why do you add 5 instead of, in the other one you subtracted 5?
So this time we are adding exit. So out of buffer system conjugate base will neutralize that, right? So base will be used. In this buffer system, this is the base, this is exit. So incoming exit will be neutralized by this guy. So we need to use 5 millimole of this. If you use 5 millimole, we're gonna use 5 millimole turn into this remaining amount. But if you use this guy, that will turn into conjugate exit. So this will increase by same amount. I did almost same approach, but except I need the concentration. So to find the concentration, mole divided by volume. But we know that volume is same for both X and base. So I do not even calculate the concentration. This is just simpler. If I have to do calculation, I have to do 2 more extra calculation. But actually we don't have to, so I just cancel right away using this number. It's supposed to be molar concentration, but you don't have to. You can just use more. The volume will be same anyway. Just try to, avoid the extra effort. Okay. If you don't have question, we're going to move on to next. So, although it doesn't have to be equal amount of X to base pair, to make it simple, let's say we have equal amount of conjugate X to base pair. Okay? And if you put a little bit of base, this much of base, then you use that much of exit, and then you lose that amount, and then that turn into conjugate base. Okay? If I put, but incoming exit is like a lot more injection, okay? Then if you put like this much of exit, then we're gonna obviously use that much, okay. If incoming base is that much, we're gonna use that much of base on the exit. So how much is okay when you use this? Well, obviously you cannot take more than this amount, right? If you put this much of hydroxide into system, now you do not have buffer anymore because you are using, all your exit. So this is the limit you can take. But before you take all of them, obviously you will have trouble. But theoretically, you can take that much of incoming base or incoming exit. So this is what is capacity, buffer capacity. Okay? So if you have a lot more concentration of both of the pair, then you have a higher capacity of a buffer. Alright. So larger initial concentration of exit and base, which means conjugate pair of exit and base, that is increasing our capacity of buffer. Which buffer system has highest capacity? You don't don't have to do any calculation. D. Because it has more concentration of acid here, and then highest concentration of conjugate base. This is highest capacity of buffer. And which one is weakest capacity, no, lowest capacity of buffer then? D? Yeah, D. Because this number is the smallest. So when we say capacity, it doesn't, so even if this guy is like a 2 molar concentration, it's determined by lowest number between two, okay? You have to have, enough amount of both of them. If you have only one kind of a lot and then you have a little bit of the other, this is limit your capacity, okay? The pH of buffer system is determined by, not determined by, but conveniently calculated by Henderson-Hasselbalch. Okay. By the way, I just keep saying Henderson-Hasselbalch, but you could still use just regular expression of equal constant, because mathematically they are equivalent. Okay, you can use that. That'll be fine. And then we saw the pH will change slowly because formula has this one as a ratio. So when you accept the acid base, it will change a little bit of that, but when it comes to the ratio, it's not that much. So pH changes slowly. But if you look at this logarithm, you will see that anytime, let's say I have acid base, just like that. But if we put like about 90% is used up. Let's say I just put a lot of, somehow accidentally, a lot of base entering body, then it used up 90% of acid. Okay? If that was too much, so it used up 90% of existing conjugate acid. That means you have around 10% remaining here, right? So when this was equal amount, this is supposed to be just 1. If you have 1 mole, equal amount, that's supposed to be 1. And log 1 is 0. Okay? Then the pH is at around the pKa. But either you receive a lot of base or a lot of acid, and they use a lot of them, and it happens to be, if this unbalance is like the other one is 10 times greater than conjugate pair, so then this ratio might be either 10 or 1/10, right? Because one component is like a lot, so this ratio might be that. If you take logarithm of this, logarithm 10 is 1, logarithm of 0.1 is -1. So that's when we have here plus minus 1. Okay? So if pH change by integer, like 1, that's when we say your buffer is no longer work as effectively. Okay? So if you use 1 or the other, and then make ratio as like a 1:10 ratio, then it's not any more effective buffer. Okay? And then this is terminology. pH range is within that range, buffer will work as effectively. Normally we say like plus minus 1. Okay? If it change more than plus minus 1, you do not have any more effective buffer. by definition, buffer is anytime you have any acid and conjugate base, or any base with conjugate acid, then you have buffer. But this should be weak stuff, okay? Weak base, weak conjugate base, or weak acid, or weak conjugate acid. But although any ratio will make a buffer, the ideal buffer will be like having equal amount. Okay? So this equal amount, that is the most ideal. Why? Because if it's equal, then this ratio is just 1. So you are just in the middle of range, and then you can just go either left or right as like a full capacity. Okay? So with that in mind, if you want to make buffer at pH 4.30, let's say this one is like a different, again different life form from the human. Human, they would like to maintain pH around 7 or maybe a little higher than 7. Let's say this is some other system that comfortable with this pH, and then we want to make certain buffer solution into that guy. So which one should we use to make that buffer solution? Ideal buffer is you have same concentration of both of them, right? Because then ideal buffer means this will be just log 1, which means for ideal buffer this guy should be equal. That means hydrogen concentration will be equal to Ka value. Because we are given pH. From pH, you can calculate H plus concentration with this formula. And for ideal buffer, Ka value should be equal to that. So this guy should be when you use certain action, that K value should be equal, similar to that number. In this case, this guy is closest to this. Okay? So let's say whatever animal or whatever creature using this system, and somehow it's using the lots of its body fluid, and you have to add more of this body fluid. You have to make it. Okay, then you're gonna have to this acid, and then take this acid and so which is benzoic acid. So let's say this is benzoic acid. This is from organic chemistry, so I'm not gonna do that. But benzoic acid plus conjugate acid of this benzoic acid. No, it's acid. It's conjugate. That's acid. So benzoic acid, and add the conjugate base, which means benzoate. Benzoate. So you bring this guy and conjugate base salt together, and then make a buffer. Then you can just inject this guy. If this guy is breathing, body fluid, you can make it.
So, because the pH is 4.30 and that's 2 sig figs, Ka value be 5.0? Or is it 5.01?
You're right. Is that right?
Just IR.
Yeah. Thank you. Yeah. So 2 sig bit. Therefore, that will be for just 5.0. You are right. Thank you. All right. Check your detail again. If you get special points, you should have. Okay. Thank you. All right. That's how you make buffer. And that's how they make the solution for human as well. Okay? They just inject something to human. When you use a lot of the body fluid, you're gonna make a buffer, something like that. Oops. So there's several ways to make a buffer solution actually in practice. I just said in the previous slide, so in that case you go to weak acid, benzoic acid, and find the conjugate base which is benzo A. That was one way to do it. Or you just pick some weak base with its conjugate acid. So that's one way to make a buffer. Another way is just use weak acid and then add strong base. Okay? Instead of mixing two weak stuff, you could use strong stuff as long as you use a little less amount than weak stuff. Okay? So when you mix weak stuff with strong, you're gonna always use less amount of strong stuff than weak one. You're gonna see how that happens. Okay? So why don't we see? We have weak acid dissociated with that guy. So anytime you mix certain amount of weak acid and mix with certain amount of conjugate base, and if you have both of them at the same time, then make a buffer, right? So what if you have just only weak acid and then neutralize with a strong base? Well, if you mix this guy with a strong base, actually we already did that. You have a lot of this guy because it's weak acid. If you have weak acid only, you have most of them actually stay as weak acid, and you may have a little bit of dissociation, a little bit. This is too much. A little bit of conjugate base, right? But if you add strong base, to here, about this much, then you're gonna use this much of acid, and you're gonna add that much of conjugate base, right? So adding strong base to weak acid actually help to create a little more of equivalent amount. If I use a little more of strong base, then I'm gonna have this much will be used up. I'm adding that much of a conjugate base. So it will be more like an ideal buffer solution. So do you see this? Yeah. So there's two different ways to make a buffer. You can start with both strong and both weak acid and conjugate base, or you just start with weak acid only, but use strong base. But this should be less than original amount of that guy. If you use a lot of base, you're going to use up all of those original weak acid. You do not have buffer anymore. Is that confusing?
Yeah.
So it'll cause less of the acid, and that makes it dissociate more. Is that what you're saying? Or am I just reading it wrong?
to make a buffer, you can just mix weak acid and weak base. That will be fine. I don't know, I've said the conjugate base. But we could start, so this is actually example. So if you have acetic acid, which means like vinegar, okay? Acetic acid is conjugate base of acetate. That's obviously buffer, but what if I cannot find the conjugate base? Because I have to make a buffer, I have to have acetate acid, which means like vinegar, and I also have to find the conjugate base. So this is maybe sodium acetate. Okay, I have to mix those two, make a buffer. But somehow when I look into my chemical, I found that this guy available. I do not have this one anymore in my stock. But still it's okay as long as you have strong base. Okay? Just in case I do not have both of them, I just bring vinegar and acetic acid and then add a little bit of NaOH. Okay? But let's say this one as a number, I have this one concentration 5.5 molar concentration in 1 liter. Then I could use strong base, something like let's say still ocean 0.5 molar. But as long as I use like less amount than that, which means 0.5 liter, then this guy neutralize half of that. Because same concentration, half of amount. So if you add this guy to this, then after that, I'm gonna have half of that still remaining as that guy. Another half will turn into conjugate base. Do you see it? Okay.
So you want
Are you-
a lot.
Are you with me? Kind of. Okay. Let's do a little more detailed calculation. So this guy dissociate as acetate and hydrogen ion, but it's weak acid. So if I just use only of this guy, most of them stay as this guy, and a little bit, really a little bit just remain as this. So this is even too much. I mean, this is really like a tiny amount, right? So if I have only this guy, this practically not a buffer, although you may have a tiny of that, so in that sense you have both of them, right? But because this is too little amount compared to that, we don't call this one the buffer, okay? So we have to create this one significant amount. Either you use sodium acetate with about a similar amount. So because if you have this chemical, you can make this amount of concentration that will be equivalent. Then it's a buffer. But I realize I do not have this chemical in my lab. But then still we can make a buffer as long as you have other strong base. And then I just use, so this consider this as concentration, okay? Concentration. If I use concentration of strong acid less than this amount, ideally half of that, half of amount of strong base, then this will consume half of that, right? This will consume half of that. So remaining amount will be only this. And that half amount will be turned into this guy. So we have an ideal buffer now. Okay? But when we have strong base or strong stuff, it shouldn't be more than weak stuff. The moment you add same amount or more than this amount, you no longer have this guy available. So that's not a buffer anymore. Okay? last slide. So how to do this? Why don't you try? I know it's all of a sudden, it might be challenging. But this is the last slide. That was pH 2 decimal. So